Today we are going to be going over how to get this particle tunnel effect. You'll see that these particles are changing color over time, and as I begin to move my mouse, the particles begin to spawn from directly where the mouse is, and if I move it in just the right way, well, we start to get an even cooler effect that kind of puts us inside of this unique particle tunnel. So how do we get this effect from a blank canvas template? Well, let's go ahead and start with just that. So here we have the go-to canvas boilerplate. Hover over the mouse, you'll see it's already working. We have all that default code that we usually use when creating some sort of canvas piece. Now what do we need to get this over here? Well, let's just go from top to bottom and remove what we do and what we don't need. So all the stuff at the top, pretty mandatory. Our mouse, well, we're going to be using mouse effects to actually move our particles over here, so we're going to keep that. Colors, we probably don't need this right now because the colors that we're generating right here on the actual piece, these are going to be generated dynamically on their own. We do want to keep a mouse move event listener because obviously we need a way to track when our mouse moves. Always keep a resize event listener so that when we resize the canvas, everything is resized accordingly. And then we have an objects, just a general object class right here. So we do want to keep this. That's all good to go. Implementation, we'll keep that. Animation loop, yada yada. We'll keep the rest of this for now. So heading back over here, the first thing we want to do is create some sort of particle. And particle is just a fancy word for dots. So you'll see we have all these dots that actually create a ring. These rings are composed of multiple dots just forming a circle. So we want to create just one of these dots that forms that ring. So the very first thing we're going to do is create a blueprint for that dot, that particle, whatever you want to call it. It's pretty common to call these particles, so we'll go ahead and create a class called particle. And then we have our constructor function, which has all those properties for each individual particle so that they can move independently on their own from one another. We have our draw function, which determines how this particle actually looks when it's rendered on the canvas. And then we have an update function, and this is typically where we update the particle's individual XY coordinates, radius, color, whatever it is, but sometimes we don't even need update, we can just use draw. So now that we have our particle object, we can go ahead and start creating actual particles to render on the screen. So instead of this generic objects let, we are going to change this to particles. And same deal right here, since we changed this to particles there, we want to make sure that we're changing it here as well. So particles is just going to be equal to an empty array on init, but we want to populate this array as soon as our page loads right here. So to populate our array, we're running through this for loop 400 times as indicated by this 400 right here. So that means we're going to basically be populating this array with 400 different particles. We actually don't need that many to start, and we're going to be populating our array with particles within like pulses, like every 5 seconds or so. But we do need just an initial ring, and we're going to start with just one ring that expands from the very center and outwards before we go and create that effect where we're creating multiple rings expanding from the center. So to create just that initial ring expanding from the center, we want to focus on this for loop where we are going to push a new particle into this particles array, and each individual particle has an x, y, radius, and color. So the starting point of each particle is going to be right in the center of our canvas, and whenever we want to reference the center of our canvas, we can go ahead and reference our canvas width divided by 2, because if we look over here, our canvas width divided by 2 is going to be right in the middle. And then we want to do the same thing for our y coordinates. So we'll take our canvas's height divided by 2, and that's going to put each spawned particle right here in the middle. But now we actually need to give it a radius and color. So our initial radius, we'll just say it's going to be static, and this initial radius is going to be 5 just to start. It can be honestly whatever you want. And our color is going to be static as well, so just a blue color. And we don't want to save the HTML file, we want to save our JavaScript file, refresh the page. Not seeing anything just yet, but you'll see if I go ahead and console log out our particles array, we now have an array of 400 objects, and inside of here you can see each individual particle, and its x and y coordinates are set to that of the very center of our canvas. So we're off to a good start, but we still need to actually render our particles on the screen. And to render our particles on the screen, we're always going to be dealing with the animate loop. The animate loop happens over and over and over again. And basically this is where we render all of our objects. So you'll see we're clearing our rect. We currently have this filled text right here that says HTML canvas boilerplate. We don't need this at all. We can go ahead and uncomment this code out right here with the generic objects. And we're going to say for each of our particles, so for each particle within our particles array, we want to call that particles update function. So update calls this .draw, and in return calls this right here. We don't actually need to call update. We can literally just call draw directly, and it's going to do the exact same thing. So you'll see we just drew 400 particles on top of each other. And these are all being animated. They're just being drawn on top of each other over and over and over again. So if we zoom in really closely, you'll see it's super pixelated just because everything is just being layered on top of each other. So next up, we need to get each of these particles actually expanding outwards in some sort of ring motion. And to do this, we need to utilize math sine and math cosine. Sine is basically a math function that returns the ratio of the size of the opposite side of a right triangle to the hypotenuse. And that ratio, when used relatively to the cosine ratio, which is the adjacent side of a right triangle to the hypotenuse, when used in tandem with that, is going to give us the exact velocity we need to get each individual circle moving in a different direction along a circle. So I'm actually going to bring this over to the whiteboard right over here to help you better understand what I mean by that. So to start, we currently have all of our particles being spawned in the center of our canvas, but we need to get them spawning in this ring fashion, this one circular fashion. So instead of being right here in the center of the canvas, we want them to eventually travel outwards to form a ring instead. So they're all going to be placed along the edges of this circle. And we're going to go all the way around until we complete a full ring. So looking at this, basically what we have to think of is how do we get the coordinates, the x and y coordinates for each of these points. Basically we're going to be editing each individual particle right here. We're going to be editing their x and y coordinates to move them individually along this unit circle. And the way we're going to do that is using trigonometry, specifically sine and cosine. So if we go ahead and create a right triangle from the center to this point right here, this means we're going to be editing this point's x and y coordinate. We'll go ahead and draw a triangle. If we go ahead and get the angle for this right triangle, so this right here is the angle we need, and we'll go ahead and say that this angle is about 1 radian. That's probably around 57 degrees. So we have 1 radian for our angle. If we go ahead and use that within a math.sine function, and then also use this within, go ahead and write this up here, math.cosine function. Well, this is going to be our result. So math.sine is going to be equal to 0.84, and math.cosine is going to be equal to 0.54. And these right here, the results of getting this angle, putting it inside of cosine and sine, and then producing this random decimal result is going to be the coordinate of this particle right here. So our x coordinate is always going to be cosine, so 0.54. And then our y coordinate is always going to be our sine value, so 0.84. And that makes sense because if we look at our adjacent side right here compared to the hypotenuse, we're going to get this 0.54 ratio. How big is this right here to our actual hypotenuse? It is 0.54 times the size of our hypotenuse, while this side right here, our y side, is 0.84 times the size of our hypotenuse. Definitely bigger right here compared to our adjacent side. So as a result, we get the location, the ratio that we need to get this along a unit circle. And if we start opening this angle up and we put that new angle inside of this math cosine and math sine function, well, we're going to get a value that is different from this. Basically, our x coordinate is going to be a smaller ratio, while our y coordinate is going to be a bit larger, and as a result, we're going to be moving upwards. So shrink this, add to the y, and we get this value right here. And if we keep doing that, keep increasing the angle within math cosine and math sine, well, eventually we're going to get every location along this unit circle. And that is going to give us all of our circles within a ring, exactly what we need to start creating that effect where everything just begins expanding outwards. So bringing it back on over here, I found a website that illustrates this concept a lot better than I probably just drew it. So if you go to mathisfun.com/geometry/unitcircle.html, you're going to get, you scroll down a bit, you're going to get this unit circle that is dynamic. I wonder if this is actually coded in Canvas, I don't actually know. But as I start moving my mouse, you can see the ratios produced by the different angles. And basically what we need is the value of cosine and sine. So things like 0.259, 0.961, these are what we're going to be using to set our particle's coordinates along this unit circle. So watch as those values change as I begin moving my mouse. You'll see cosine produces a negative result now because we're on the negative side of the circle, but sine is still positive because we're on the upper half of the circle. If I go back, everything is positive because we're in that upper right hand quadrant. Same thing as I go down. Eventually, if I go to the third quadrant over here in the bottom left, we have a negative value for cosine, negative value for sine, and that is just going to give us the exact value along this unit circle. So in whole, if you would like to get a better understanding of cosine and sine, be sure to check out the video on circular motion. I go into this in a lot more detail. It's probably a little easier to understand than me just kind of freeballing it like I am right now. But just know that we just need to get the points along this unit circle, and to do so, we are inputting a value into sine and cosine degrees, but we're actually going to be using radians, and it just outputs a result that is going to be the x and y coordinate we use within each individual particle, and that's going to give us that ring result. So without further ado, let's go ahead and put this into practice. So if we want to create a ring with all the circles that we have now, so we're just going to start with creating a ring that doesn't move or anything like that. Not everything should be canvas width divided by 2, and not everything should be canvas height divided by 2. Instead, we're going to add sine and cosine functions onto these values right here. So first thing first, since we're going to be doing a little bit of math within canvas width divided by 2, canvas height divided by 2, it's always good to create a constant or some sort of let variable instead. That way we just get a cleaner understanding of what exactly we're doing and assigning to a variable. So our x coordinate is going to be canvas dot width divided by 2, and of course our y coordinate is going to be canvas height divided by 2. And now we can replace canvas width divided by 2 right here with x, canvas height divided by 2 with x, or y, excuse me. Just a little cleaner, and we're going to be doing some math here that creates that ring effect. So to create that ring effect, we are going to be using math.cosine and math.sine. Let's go ahead and start with math.cosine. So the first thing we need to do is determine how many radians actually make up a complete circle. And if we go ahead and start reaching the very end of this by scrolling to the fourth quadrant, you'll see within the parentheses right up there with cosine and sine, we're around 6.178. Well, if we get to 6.28, that is actually pi times 2. So a full, just going to write this out in comments so you remember, full circle is equal to pi times 2 radians. That is essentially 360 degrees. So since we have pi 2 radians, we need to divide that by 30. And when we do that, we're going to be able to get the angle for each individual particle. And using that angle, we can get the x and y coordinates that we want to add on the particle to create that ring effect. So if we say a radian for each iteration of this loop is going to be equal to math pi times 2 divided by 30. So if we go ahead and console log out our radian value right here, you see that it's going to be 0.2094. So if I go ahead and copy this and multiply it by 30, well, we get around 6.28. That is the full circle that we're looking for. So we're on the right path. We have the distance for each angle we're going to be using within this unit circle. So now what we need to do is onto our canvas's width, we are going to add on math.cosine radian. And we're going to do the same thing for our y value. We're going to add on a math sine radian, because when we're using sine, that affects the y coordinate, as you can see right here. So if we save this, go back to our canvas piece, well, no changes just yet. And that is because when we add on the value of math cosine radian and math sine radian, Well, we are only getting a value anywhere from -1 to 1, and that is not big enough to make any change right here that is noticeable. So typically what we do is, since these are ratios anywhere from -1 to 1, we can multiply it by a larger factor, such as 10, 30. That should give us a pretty large ring. We'll do the same exact thing for sine right here. And you'll see that moved very, very slightly, but still things are not looking too good. Everything is still being overlaid on top of each other. And that is because we are adding on the same value of math cosine radian and math sine radian for each individual iteration of this loop. What we need to really do is, for each individual iteration, we need to make sure that the radian is being changed. And to actually change the radian, what we want to do is multiply it by the value of I. So if we go ahead and multiply radian by I, we're going to be incrementing it each iteration of this loop. So first run through of this loop, we get the original radian value, which was something like 0.2. Second iteration, we get 0.4. Third, we get 0.6. If we look at, not this, but if we look over here and look at our radians, if we start at 0.2, we get this coordinate. If we go up to 0.4, now we get this coordinate. If we go up to 0.6, we get the next coordinate. So you can kind of see how this is working. We're basically incrementing the value of math cosine and math sine to produce coordinates for our x and y values. So if we save this, now we're starting to form some sort of ring. And we can make this ring even bigger by incrementing this value right here. This is kind of like the radius that we are implementing for each individual particle. So what we can do to make this a little more clear is create a constant called radius and just set it to whatever we would like. And this can actually go outside of the for loop, since it's not going to be changing at all. And then replace our 30 right here with that. So you'll see if I begin changing this radius now, we get a larger and larger ring. Go to 150, we get an even larger ring. And you can really play around with this a lot just by dividing the radius right here within your assignment to x. And you're just going to get some really wild results. So instead of dividing by like 30 or something like that, go ahead and divide by I. And you'll see you start getting curves and stuff along the lines of that. That looks like a Fibonacci or golden ratio. I'm not really sure what that's even called, but let's go back to where we were. Just adding on the radius. And this is a little big. Let's go ahead and just focus on 100. So this is off to a great start, but we want to keep things directly in the center and then expand them outwards. So how do we actually start moving these in the right direction? Well, instead of initializing each individual particle to its initial position, we're going to go back and put them all in the center. But this result that we're getting from math sine and math cosine, we're actually going to store as a particle property, as a velocity property specifically. So if we change math cosine and math sine, get those results and start adding them to our particles' x and y coordinates as a velocity instead, well, we're going to get that effect of everything expanding because we have the perfect ratios for each individual particle that is going to push them in the right direction. So I'm going to go ahead and make a copy of this, put it in a new tab, just so I have it for reference later on, and we're going to go back to where we were initially with all these spawning in the center at canvas width divided by 2 and canvas height divided by 2. So directly back to where we were, probably not too much progress, but it's all good. So if we go to our particle, we know that it takes an x, y, radius, and color. We also want this to take a velocity, and this is basically the speed at which the particles are going to be moving at. So we can say this dot velocity is equal to velocity, which is going to be this guy right here. Now we have to make sure that we are passing through velocity as an argument whenever we are creating a new particle. So velocity is going to be an object with an x and a y value. So an x velocity and a y velocity. So the rate we want to move our particle on the x coordinate is going to be the result that we get from math cosine. So we'll go ahead and put that in there. And then the rate at which we want to move our y coordinate is going to be math sine. And we'll put that right there as well. So now, whenever we console log out our particles and view this in the console, look inside one of the arrays, we now have a velocity for each of these individual particles as well. And if we go through each of these individually, you'll see that they are different. And these are basically the values of each particle as it would be along that unit circle's edge. So what we can do is, inside of update, we're going to draw each individual particle, which uses an x and a y coordinate, So we're drawing that out, but we're going to be editing our x-coordinate, and we're going to be adding onto it our velocities x-coordinate. And this is exactly what we just put in here using math cosine. So onto x, we're going to be adding our x velocity. And then we want to do the same thing for our y-coordinate, but instead of using our x velocity, we're going to be using our y velocity. So if we save this, nothing happening at the moment, and that is because when I was explaining this earlier, I said that we could use draw because all draw is responsible for is actually rendering these circles on the screen. But now that we are actually editing our properties for x and y within update, that is what we want to call it instead. So we're drawing our circle, we're editing the properties, and then we are redrawing it since it's inside of this animation loop. So instead of using draw, we'll change this to update. And now we get that ring expansion effect that we're going for because our velocity is equal to those ratios that we produced from sine and cosine. And that's really all there is to it to get that initial effect. So to actually get something that looks like this, we need to make sure that we're continuously spawning particles over and over again. So to get a function that runs continuously in a loop, we already have animate, and that uses request animation frame. And request animation frame runs as quickly as possible for frame rate reasoning. So instead of using animate for a function that calls itself over and over again to basically create more rings, what we're going to do is create a new function, and this is going to be called generate ring. And inside of this, we're going to use set timeout. Set timeout is a function that basically calls another function after a period of time has passed. So this period of time is basically the interval in which this function is going to be called and looping through itself. So 1000 is basically equal to 1 second. I believe it is. Call me out if I'm wrong. And the function we want to call is, well, generate ring. So we're going to be calling generate ring every second. And we can test this out by inside of generate ring, outside of set timeout. If we go ahead and console log some text, anything could just be like go. We should see text right here, and we're not. And that is because we actually need to call this function before it executes. So if I go ahead and save that with generate ring at the bottom here, you'll see go is being called just about every second. So now that we have something calling itself every second, this is where we're going to be pushing in particles. And as we push in particles, we are already updating their x and y coordinates to create that ring effect. So if we just keep calling this and pushing particles into our particles array continuously, we're going to get that effect of multiple rings. So what we can do is just copy this for loop right here, paste it into our generate ring function. And you'll see now we have something that spawns continuously. So if this keeps running over time, eventually it's going to crap out because we're going to have so many particles on the screen and even off the screen that the canvas is just going to keep trying to render them. You'll see if we console log out particles every iteration of generate ring, let's go ahead and console log out particles, that this array just keeps increasing and getting bigger and bigger by 30 particles each time. Eventually this is going to get so big that Canvas can't even handle the processing for this. So to make sure that these particles are actually disappearing after some time has passed, we're going to give each individual particle a time to live. This is the amount of time it actually has before it is removed off of the screen. So within our particle class, we're going to add another property called TTL, short for time to live. This is going to be equal to, we'll just say 100 to start. And as the particle updates for each frame we're actually rendering this particle, we are going to remove 1 from this time to live property. So time to live is going to be decreasing, and now we can use this property as a way to determine which particles should be removed off the canvas and which shouldn't be. So if we go back down into our particle render loop right here, we can say for each particle, which we're already doing, if the particle's time to live is less than 0, meaning that we are ready to take it off the screen, then we want to select our particles array and splice out this one individual particle, which we can do by selecting the particle's index within the array. So within for each, this for each function takes a second argument, which is going to be the index of the particle that we're looping through. So a nice little helper function right there. We want to splice out the particle at that index, and we only want to splice one position from the specific index as indicated by this 1 right here. And then else, if it's not less than 0, we're going to continue updating. And that's just going to make sure that we're only running one of these two. So you'll see eventually when 100 has depleted down to 0, that we are removing all particles from the screen, all particles from our particles array. And that way we're going to get something that is performant. But obviously we want these to last a little longer. So instead of setting this equal to 100, we can set it equal to 1000. And that should allow everything to get off the screen. And eventually these are going to be removed altogether so that we can continue getting a performant canvas piece. So performance aside, let's go ahead and add in the mouse event listener to spawn the center of all these rings, all these particles from the middle of our mouse. So if we scroll up with the canvas boilerplate, we already have an event listener called mouse move, and it's setting mouse X and mouse Y equal to the position of the mouse. Well, what we want to do is, instead of spawning each ring as canvas width divided by 2 and canvas height divided by 2, we want to spawn each ring as our mouse's X and Y coordinates. So what we can do is say, instead of generating a ring at our canvas width, generate it at our mouse X and our mouse Y, two properties that are being changed within this event listener right here. So if we do this, save it, we are still spawning at the very center, because when we run this init function, we are setting the center of our ring to be canvas width divided by 2 and canvas height divided by 2. But when we start to move our mouse, now the rings are being spawned at the center because we're generating a new ring at our mouse X and our mouse Y. So this is kind of slow. Let's go ahead and speed it up by decreasing the amount of time to generate each ring. It's looking a lot cooler. I think we can go even lower to 200, and I think I am really liking that. That gives us a really, really cool tunnel effect. So we're almost done. Now all we have to do is really affect the coloring of this, and this is going to bring the piece to the next level, exactly what we're looking for when looking at something like this. So first thing first, I love changing my background to something dark instead of just white. So instead of clear rect, which just clears the whole canvas each animation loop, we are going to use fill rect instead. And whenever we use fill rect, we have to set a fill style. Otherwise, we're just going to get the last used fill style, which is going to be the blue of the dots. And we want to set this to RGBA 0, 0, 0, which is going to be black, basically. And then our alpha value, which we can set to 1. And that's just going to give us a pure black background. But if you'd like to add some sort of trails and like fade effect, then you want to change this alpha value to something lower, something around 0.1, maybe even 0.05. And that's just going to give you a really cool fade effect. I think I like that a lot, so I'm going to go ahead and keep it. But if we want to change the color of each particle each time we spawn a ring, well, we're going to have to focus within our generate ring function. So right now we're spawning everything as blue. Let's go ahead and use hue, saturation, lightness. So the first value for this is any value 0 to 360. We'll start off with 0. Second value is going to be our saturation, which affects how deep a color is. We'll just set it at 50%, which is pretty common. And then our lightness is how bright the color is. We'll set that at 50% as well. So if we start off with just this, we get this nice red color, but we want this to change for each iteration of generate ring. So what we really have to affect is 0 right here. We have to go between 0 to 360 and back down over time for each iteration of this loop. So the easiest way to do this is to create a let called hue, and we're going to set this equal to 0. So if we set our hue variable to this hue string right here, and if we're using a variable inside a string, we need to make sure that we're using a template literal. So we'll change these quotations to backticks and then integrate our variable in here by using $, opening curly bracket and then closing curly bracket. We're going to get the same effect, but now we have the ability to change this hue variable over time. So for each iteration of generate ring, what we can do is add on 1 to our hue value, which we can just do by saying plus plus. Anything with plus plus on it is just going to add 1 onto the current value. So you'll see over time we are actually getting our color changed, and this isn't quite apparent. It takes a little bit of time for the color to actually change. So instead of just adding on 1, we can say hue is going to be equal to itself plus 2. And when we do that, our color should change quicker. You'll see it goes a little bit quicker than before, going from red to orange to yellow and so forth, getting this really cool effect. But eventually when we hit 360, we're going to get these black circles, which we don't really want. We always want to be going to and from some sort of bright color. So a super easy way to affect our hue over time is to use either a sine or a cosine function, because those return any value from -1 to 1. No matter what, it's just going to keep pulsing between those two. And if we multiply that by 360, well, we're going to get any value from 0 to 360 continuously over time. But in order to do that, we need some sort of radians constant. And I believe we already defined radians elsewhere, so I'm going to make sure that this is something different. I'm going to call this hue radians instead, set this equal to 0. And now for each iteration of our loop, I'm going to set hue equal to math.sine hue radians. And if we want some sort of different value for our hue every time we're running through this loop, we need to make sure that we're increasing the value of hue radians. So what we can do is, at the very end of our loop, we're going to add on 0.01 into our hue radians. And let's go ahead and console log this out to see exactly what we're getting. So for each iteration of generate ring, if we console log out hue, you'll see our hue is increasing over time. And this is looking really good. So these values right here are going to range from 1 to -1. And when we multiply this by 360, we're going to get any value from 0 to 360. And we can begin using this as our actual hue to spawn each of these individual particles. So right now, our hue is just equal to math sine hue radians. We want to make sure that we are multiplying hue by 360. So we can do that right here. And now our hue is actually going to change over time. And you'll see eventually once our console log hue, once our radians actually reaches 1, eventually it's going to start going downwards towards -1. And once we hit -1, our colors are going to break because we can't have a hue value that is negative. We need to make sure this hue value is always positive, and to do so, we can use a simple math function called math.abs, which stands for absolute. This is going to make sure that every time we have a negative value, we change it into a positive value. And that's just going to make sure that we go down to 0, not -360, but when we hit 0, we're going back up to 360. So we'll go down to 0 to 360, back and forth, back and forth. So if we save that and refresh the page, now we have a fully functioning canvas piece that emulates something like we have over here. So what you can do to start making this a lot better is just start playing around with the rate at which things are spawned. You can play around with the radii of the circles, the rate at which our hue is changing, and also the speed at which each of these circles is spawning. We're already going pretty fast right now, but we can make these a lot faster. Let's go ahead and see what we can do with this real quick just for fun. So I'm going to go ahead and increase our velocity each time we spawn a new ring of circles. You'll see we get this really wild effect right here. Probably go ahead and do something like 3 instead. We're spawning a lot, so I want to spawn maybe just a little less. Go ahead and spawn 20 particles per ring instead. And now I'm only spawning part of the unit circle because right here we're still using that initial 30. So what we can say is particle count is equal to 20. That way we only have to change this value in one place. So now we only have 20 particles being spawned at a time. If I really wanted to go crazy with this, I could do 100. Now we have 100. I kind of really like that. I think I'm going to stick with this. And I just want to make sure our velocity for our initial spawn is also going to be 3. We're getting really freaking crazy now. Oh boy. And I'm going to make sure that our initial color is HSL 0, 50%, 50%. You technically don't even really need this initial spawn, so we can actually just get rid of all this. I don't even know what I'm doing. There we go. Cool. All right, so I'm actually going to call it at this. This is something I'm pretty happy with. I think it looks really cool, but I would love to see exactly what you guys have. Be sure to post your creations in the comments, create a code pen and just leave it, and show me that you can do better than me, because I know you can. So that's it for this one, guys. If you would like to check out more tutorials, more HTML Canvas, more web app tutorials, be sure to head over to chriscourses.com. This is a learning education platform that I created for web developers like you and I to help learn web development, whether it be Canvas or how to create web apps like I created right here. It teaches you how to log in, create usernames, registrations, whatever it is. This course right here, Web Apps for Beginners, will teach you how to do that. So check it out if you're interested, and be sure to ask me any questions you might have. Otherwise, that's going to be it for this one. Hope you enjoyed, and I'll see you next episode. Peace.